Okay, hi. My name is Kim Næss. I need to find a way to adjust my voice because this is going to be too high, so this is going to be interesting. Yeah, Kim Næss, working for Hitachi Vantara.
And my name is Elena Salova. I also work for Hitachi Vantara.
And we're going to have a little bit of fun with trains. First off, I have to apologize. We were actually really hoping that we were going to be able to have like a train set outside with like IoT sensors and model trains and like really show off some of the cool thing we can do. Unfortunately, we didn't find anything that was suitable. And the Hitachi Rail, we even went and looked through some contacts to see if they even have one, but no. So next year, maybe. So we're just going to be speaking about the trains. And key topic for our speak is that Hitachi does, of course, both trains. We have the industry knowledge of building trains, but we come from the technology part of Hitachi, where we do a little bit closer. Okay. And we try to be the technology part where we can actually do the data collection, the data integration, and the data science to give you some of the insights into how we can make the trains perform a little bit better. So, when I first started off in Hitachi, this was what I knew. So I thought about Hitachi as TVs and hi-fis and a lot of fun gadgets and also power drills and yeah. But Hitachi is really an industrial conglomerate that does almost everything. Everything from medical equipment to trains to power tools to TVs to more or less everything you can think of, Hitachi actually manufacture. And that is a great way to do, a great thing to do, because whatever we do as a data scientist, as data engineers, working with IT, we have to serve the different industries. We have to serve the different businesses. So what we do in technology might be a little bit generic, but when we actually liaison with the business and we need to create insights for the business, we need to talk to the subject matter experts with whatever company we're working for. So working for Hitachi is kind of interesting because we always have an industry that can match some of our customers. And talking about AI and robotics, we are at the 4th level of the Industrial Revolution. However, the Industrial Revolution started in 1712. And in 1712, the workers at different places, they were scared that the steam machine would steal their jobs. Rightly so, right? Because the mechanization of that working process was actually removing jobs. And today we are here about 300 years later, and we're still talking about AI and robotics, a new industrial revolution, and it's still designed to take people's jobs away. People are fearing for the jobs to go away, and rightly so, right? Because some of the things that we will actually be building are going to be taking people's jobs away. But people will adapt, people will change. We always have, we always will. Back in 1712, we were about 800 million people on the planet. Today, we're about 7 billion, and still unemployment is pretty low. So whatever we do, we still need to think about how to adapt and how to change. So I never think about change as something that I fear. I think about something that is exciting, something that's cool. Some of the people that I really look up to is Elon Musk. And what he's thinking and what he's doing is visionary for me. What he's doing with cars is one thing. What he's thinking about going to space and going to Mars is another one. You can think what you want about global warming and Greta Thunberg, but we only have one planet, and if we fuck it up, we're gone. So what about having a backup? Going to Mars could be a good idea, being an interplanetary species. One of the things about the Tesla, and I want to make a remark here, is that Tesla and what we're doing is that we're innovating, doing digital transformation with data. Applying data to whatever kind of business that we are in is what is actually changing the businesses. And Tesla is doing that. I think one of the most common example is that you think about Tesla as the Autopilot, and the Tesla Autopilot is actually each day collecting more data than what Google has done since they started with autonomous driving. But the most impressive thing for me is that Tesla just started off the Gigafactory 3 in Shanghai in China. 1 year after that they got the grant to build a factory, they were able to take the data from all of the robots in Fremont in California who were building cars and just put up the same robots in a new factory, in a new facility, and they're building new cars at the new site 1 year after. There was nothing there, and now they're building cars. And that is being done by, of course, getting data to the right place and making sure that the AI and the robotics can do the same kind of job. Now, what can we learn from this? So within Hitachi, we manufacture trains. These are our latest model, due to be sold, I think, is in Italy next year. And with any kind of industry that you're working on, you need to find something that you want to modernize. The rail industry, they were in, I guess, in dire need of trying to adapt and trying to change, because what they are doing and have been doing for about several hundred years with trains is an old model of working. And what if we can do some of the same principles and think about some of the same principles as you're doing with Tesla, is looking at what kind of sensors can be attached to a train and what can we learn from those sensors. So in essence, they wanted to modernize and improve the rail reliability and availability, but also to do predictive maintenance and schedule optimization. How can we make the trains run more efficiently and take them out of service when we need to? And the growth of the rail industry has been huge in the last few years. This is numbers from the UK rail, and the forecast growth is going to be double. From the last 30 years, it's doubled. In the next 10 years, it's going to double again. Now, how do we keep up with that? I'm guessing, I come from Norway, and in Norway, it's kind of a joke to see if the train is actually coming or not. I think it's the same here in Sweden. It sounds like it. And one of the, I say, proud things of working for Hitachi is that there is this thing, if you live in Japan, anybody, I think we have one here, he's from Japan, and you can verify if this is true or not. Because in Japan, if the train is late, they actually have to go on national TV and apologize. That happened like last time about a year ago. You're like more or less on time all the time, always, right? Yeah. And how can we take some of that knowledge and apply it to other countries? So we're trying to do that here in the UK. This is where the example and where the data is from. And this is just one of the things that we're highlighting and seeing with regards to maintenance optimization, trying to predict when you're going to do maintenance. When you have a car, and that car is being taken out of service, that's based on the knowledge of that car industry. When will you replace the diesel filter? When will you replace all of the parts of the engine at a certain period of time or kilometers, right? But that doesn't take into account my driving, how I'm driving, or the weather conditions of where I am. It's a generic recommendation to change everything per 20,000, 40,000 kilometers, right? But it makes a difference how I drive and the wear and tear of those parts. So you're actually replacing, with planned maintenance and condition-based maintenance, you're replacing a lot of parts that is still functioning and still working too early. And that is not a good economic decision. The other one is that you can wait until it actually fails, and that's a little bit worse, especially if you're on a train with a lot of people or in a car. So how can we use data to actually do that a lot smarter? Oh yeah, and technology, could we have done this earlier? Some of the facts here is that the amount of data that we take from the trains, if you were to store them, the data, it would take about $2.5 billion in 1990 to do this then. And I think we did some calculations, and that was like 1% of the revenue of Hitachi in 1990. So you wouldn't really do it then. It's the speed of the compute power that we have today and the low cost of storage that enables us as data scientists and data engineers to find those insights as we do today. They couldn't do this earlier. So this is one of the train sets that we have in the UK. And this is a subset of the sensors that we actually have on the trains. And we're collecting those data from those trains in real time, and we're sending it in real time. And we're also doing data dumps at the stations when they're stopping by and when they've been taking out for maintenance. The architecture, we can show you more of this if you want to come to our booth later on as well, is a collection of tools that we're using. So you can see Pentaho, which is the technology part, the data integration part that we are working with, is the one that is actually collecting all the data from IoT streams. And then we're putting that into several different repositories with a MapReduce and an HBase and a time series database as well. And we're also using Impala for analytical database. All of these are components that we are building in order for us to get to the end goal, and that is delivering the data sets that is of value to the data scientists so they can do the prediction from the sensors. With the amount of data that we have, of course, one person looking at a set of data from one train, you can spot some clustering of data to show you some kind of insight, some anomalies. That will always be possible. But what if you have 48,000 sensors? That is kind of impossible. And this is why we need to start thinking about how we can actually get those data and put the correct mathematical algorithms to gather the inputs that we need. And of course, we can work together. We can work together with another train company. But what's unique about this one is that when we are delivering the trains as well, we have that rail expertise. We know how the trains are being built. We build them ourselves. We have first-time access to the data, to the rail engineers who are actually building them. We are also having the technology part, the data integration part, the machine learning part. So we do more or less everything in the ecosystem in order for us to get to the knowledge of the trains. And as you can see, it's quite a lot of data that's been collected. All of this data has been collected since, I think, 2017. Yeah. And we're starting to find some insights. And I'll hand it over to Elena to talk a little bit more about them. But really, what we're trying to do is that when we started looking at all of these data, there were some goals in the beginning of how we can actually optimize the trains, but a lot of the use cases is also things that you find when you start looking at data, because your data will tell you a story when you start analyzing them. When you start looking at your data, cataloging your data, making it searchable, that is when your data can tell you a story. So some of the things that we started off with and thinking that we were going to be able to do predictive maintenance, schedule optimization, some of these use cases were actually thought of afterwards, when we actually found the data. So Elena, you want to talk to us a little bit more about how we actually do this and some of the findings that we had from the data?
Sure. So in our pilot project, we are focusing on the predictive maintenance for the components of the trains. And one of the very good prospects for this was door maintenance. And well, why doors? This is a report from the network rail, and this is a report about the delays that were attributed to the technical fleet failures in 2018-2019. And network rail actually attributed 390,000 minutes delay due to the door and door system failure. It's a second common delay. And well, why it's so important? So imagine there is a train, it's staying on the platform, and one of the doors cannot close. This train actually cannot move anywhere. You shouldn't be driving this train. You need to summon your maintenance team, they need to fix the door, and well, it definitely will take some time and the train will be delayed. But it also, like, not only this train will be delayed, it can cause a cascade delay in all of the other trains coming to the same platform because, well, the track is occupied. So this is a very, very big problem. Another thing that we now have very good failure reports about why there was a door failure. I have a lot of data coming from the sensors, from the doors, and from the place that surround the doors. And this issue is also very well known to the maintenance team. So we really wanted to focus on something that would tangibly decrease the maintenance time for the train and would really improve the overall efficiency of the maintenance team. So in this use case, it's actually two use cases. The first one is a failure prediction, because you really want to predict the door failure because before they occur. You want to spot some anomalies in the data that could lead to future door failure, and of course, overall, you want to improve the reliability. But the second use case is also very important, is about the maintenance schedule improvement, because the maintenance team has to go all over every door in every train every day, and they have to check all the doors. And you can imagine now we have a lot of sensors in the doors and a lot of data coming from it. So basically, if the data is the same as it was the day before, and the day before the door was fine, probably you don't need to check it. So there is a lot of redundancy and inefficiency in the current maintenance process, and it can be really improved by using the data that you already have from this train. This is a CRISP-DM methodology, and I don't need to explain that. You all know that. But one goal for us in this project was to actually make this thing work. And how are we going to achieve that? Is that we are working really closely, data scientist team, data engineer team, and domain expert in all of the 3 first phases when we're identifying the use cases, when we are understanding our data, because there are 200 terabytes of this door failure data coming to us, and you shouldn't expect just put this on the lap of data scientists and they will solve magically all the problems. That won't happen. You need to have a domain rail experts working with you and trying to understand what are the important data sets, what are the important features, how we should proceed forward, and what should we actually do with this data to predict the door failures. So the first 5 stages of this CRISP-DM process is going to be like the whole pilot project, and after that we will move to the deployment. And how are we going to bring the digital maintenance to life? First, of course, we will train our machine learning algorithms, and we will have a failure prediction and anomaly detections. But what's important about that after that, of course, we will apply these models on the streaming data, but what's important about that we are not only thinking about, hey, we will have encoder, decoder, anomaly detection model, and it will solve all our problems. We are thinking about the KPIs that will be important for the maintenance team, and how are they going to use the predictions from the model. So in this case, we will have we are working on a health index assessment. So basically, each door is having a health index. And by this health index, the maintenance team can easily understand what's the condition. So if there are some smaller problems with it, probably it can be indicated in this health index. And in that case, the maintenance team can prioritize to fix this door, maybe not right now, but later. But if, later in the day, but if there are some significant problems with it, the door should be fixed right now, they will be notified of it. So, yeah, we're not thinking only about the models here, but also about the business outcome of the whole project. This is one of the very, I think it's personally my favorite one. I really like this use case. But also you can think about the railroad industry is very big, and you can think about it from kind of a different side. So I'm going to talk a little bit about the supply chain operations. So imagine you're in supply chain operations of a big rail company, a rail infrastructure company, and what are you doing? You're supplying the infrastructure and the materials for all your construction projects, and you need to be able to deliver all the materials in a timely manner. Your challenges are that you need to actually predict what type and what amount of materials you're going to need in all of your yards and all of your sites. And that can be quite a task. Also, you really would like to have an efficient network utilization. You don't want your trains, your cargo and freight trains going just half empty, right? You want to be them full and also on schedule. So the 2 business use cases that are working here, they are very connected. So the first one is improve the forecast accuracy for the supply chain team. So they want to forecast how many materials and in which places they need better to improve the, first, of course, to negotiate better with the suppliers and not to have some kind of problems with a lack of materials in certain places. Second one is schedule for the trains, because for each of the trains there is significant cost associated with it. The driver, the power, the staff, and all other costs. And you want to efficiently utilize all of that resources that you have. So this is an example of a like network utilization. So it's a like daily service from one big yard to another, and the left-hand side graph, the blue one is length utilization, and the orange one is the weight capacity. And you see that most of the trains are less than 20% filled, which is a huge inefficiency. It can be really improved. On the right-hand side, there is a graph of the actual number of trains. That's the like high red line, and there is also a like required amount of trains, which is a blue line, and you can see there's also like a very big gap. So you don't need that many trains going all over the place. You need just to better schedule the one that you have. What about the planned and actual quantities? There's a planned quantity for each of the material during each of the maintenance and construction process, but there are also the actual quantities. And there is a question like, do you want to have more or do you want to have less? You definitely don't want to have less, but how much more do you need? Because you don't need this materials just lying in your backyard and without any use to anyone. But you also need to be prepared for like sudden increase in demand, because maybe there is a delay in your project and now it's moving not as you expected. So in order to predict these demand cases, first we started with a like classical statistical approach, autoregressive ARIMA models, and autoregressive integration moving average, and it's nice, and it was really used for a long time in economics, especially when you're trying to predict supply and demand. But it was very good for predicting supply and demand during the longer periods. But it couldn't predict some intermittent demand, because sometimes you have demand in, let's say, pellets or ballast, and it's not continuous. In order to accommodate for that, we moved to the second, also statistical model, Croston model. It was proposed by J.D. Croston in 1972, I think, and yeah, it's also widely used in economics to predict the supply and demand, especially intermittent demand. So you're predicting the intervals between the demand periods, and you're predicting the level of this demand. It was, again, okay, and it worked for some of the time periods, but unfortunately it couldn't capture all the things and all the problems with sudden demand, when you suddenly need this amount of materials in certain yard, and it's really big problem because you have to move all the trains there. So then we moved to long short-term memory network, and that worked really well for these use cases, especially when you factor for the different types of work that you have. And to do that, we had to work really well with the domain experts, so they would explain us what are we trying to predict in what categories. Yeah, I guess that's it from me. I'll pass to Kim for some closing remarks.
Yeah, and just so one of the things, I think Hitachi Rail actually went to some of the users or some of their passengers, asking for some of their experiences afterwards, and some of the feedback that they got from the customers after we've been implementing this, and they've been running in the UK for the last 2 years now, is that the stability of these trains have been a lot better than before, and they've also had feedback from customers saying something like, well, now I have time to have have breakfast with my kids in the morning. I have more time with my kids, because however way you look at it, we're actually bringing something that is of value to all of the passengers. We want to make people travel more safely and more efficiently, so that you have time to do more of what you actually want, because nobody actually wants to be commuting, do they? It's what we have to do it, we don't want to do it. On vacation, of course, but not something you want to do for day to day. So, yeah, just some closing remarks. How many heard data is the new oil? I hope everybody heard that. Being a Norwegian, that's like, we still make a lot of money on oil, but yeah, data is really valuable, and data is really valuable when it's a curated data set, when it's something that is brought to life, and that it's something that you can actually get insight into. And the most valuable data sets are the ones that are like that. They are curated, but they are not like oil. They do not deplete. Mm-hmm. They are renewable. They are there forever. They do not pollute in any way. They are there for us to actually get value. And there's a lot of different use cases where we can actually see data brought to life. But what we see in a lot of the projects that we start off with is that we have a lot of issues. And the issues are that we are still locked in a lot of silo thinking, and we are still locked in a lot of regulations, access violations, and lock-in. And there's a lot of data that we cannot access. So the things that we want to do is that we want to help, like we did with Hitachi Rail, and there's a lot of different use cases as well, is bringing that data back to life. Because however way we start off with projects, I guess especially with data scientists, one of the things that I hear the most is that data scientists are a bit tired of trying to get the data. They are not too, it's not the most fun thing you do, writing SQL or writing Java. So getting the data sets and having readily available data sets is something that you want to have more. And to do that and to build that and to actually have something that we call data ops is that you want to be able to automate the capture of data to make the data available to you at the right place at the right time to the right people in an automated fashion as often as you can with the right kind of access rules to it. When we do that, we can access any kind of data that you want, and we can build it to any kind of role that you have in your organization. We're building that agility that enables you to have data, but have data available and updated at any given time in your organization so that you as a data scientist can work more efficiently with the things you love most. And that is modeling the data. With that, I think we are finished. Thank you for listening.